What does it mean to live in a universe we can measure so precisely, yet understand so incompletely? For centuries, we have looked upward and told ourselves a comforting story, that the heavens obey order, that every light has a place, that with enough patience, the unknown will gradually surrender its name. And often, that faith has been rewarded. A falling apple led to planetary motion. A trembling lens revealed distant galaxies. Equations written in silence described storms of stars long before a telescope confirmed them. But every so often, the universe answers our confidence with something stranger. A signal arrives and never returns. A star flickers, as if something impossible is crossing its face. A region of space appears too empty, too cold, too large for our models to hold. Galaxies spin with the speed of objects held together by an invisible hand. And beyond all of it, beyond the matter we can touch and the light we can trace, some hidden force keeps pushing the cosmos outward, faster and faster, as though reality itself has made a decision we were never invited to understand. These are not ghost stories. They are observations, calculations, data points gathered by ordinary human beings, working late nights in observatories, university labs, and control rooms filled with the hum of cooling fans and fluorescent light. Yet the feeling they leave behind is older than science. It is the feeling of standing at the shoreline in darkness, listening to waves, knowing the sea is there, and knowing you cannot see its edge. This journey is not about proving fantasies or chasing easy answers. It is about the fragile, stubborn beauty of inquiry itself, because sometimes the most revealing discoveries are not the ones that explain the universe, but the ones that remind us how much of it remains beyond our grasp. And perhaps that is where wonder truly begins. What if the first crack in our confidence was not a violent explosion, but a star that simply refused to behave? Far from Earth, in the direction of Cygnus, a point of light began telling an unusual story. It was not brighter than the others. It did not announce itself with fire. It merely dimmed in ways no one expected. For astronomers studying the quiet rhythms of distant stars, the pattern felt wrong from the start. Not elegantly wrong, as in a puzzle waiting for the right equation, but deeply irregular, like a sentence interrupted halfway through. The star came to wider attention through the patient eyes of citizen scientists reviewing data from the Kepler telescope. Among thousands of ordinary light curves, this one looked almost alive in its unpredictability. Sometimes it faded a little, sometimes much more. At one point, its light dropped by an astonishing margin, far deeper than the brief, clean dip caused by a planet passing in front of a star. There was no steady timetable, no repeating orbital signature, no simple mechanical explanation. Astronomers began with the language science trusts most: dust, debris, comets, instrumental error. Each possibility offered something, then failed somewhere else. A cloud of material might block the light, but where was the expected heat signature? A family of shattered objects might create irregular shadows, but why this pattern? And why this star? The mystery widened not because scientists rushed toward fantasy, but because the ordinary answers seemed incomplete. Public imagination did what it often does when uncertainty opens a door. Some wondered whether this strange dimming could be evidence of an engineered structure, vast and deliberate, orbiting a distant sun. Most researchers remained cautious, and rightly so. Extraordinary ideas are easy to name and hard to justify. Still, the fact that such speculation could briefly survive says something about the event itself. The star had wandered so far from expectation that even disciplined minds had to pause. And maybe that is the deeper story. Not whether the answer is exotic, but how quickly mystery reveals the edges of our confidence. We like to think the universe is readable, that every strange signal will eventually settle into familiarity. Yet now and then, a distant star reminds us that knowledge does not move in a straight line. Sometimes it flickers. Sometimes it hesitates. Sometimes it leaves us staring into the dark, wondering whether we are witnessing an explanation delayed or a reality larger than our habits of thought. How do you describe an emptiness so large that it begins to feel like a presence? Imagine looking into the night sky and finding not a cluster, not a glowing river of galaxies, but a wound in the map, a region so vast and so strangely quiet that it seems less like a place and more like an omission. Astronomers call such structures voids, and in the architecture of the cosmos, they are expected. Matter gathers unevenly. Gravity pulls some regions into crowded filaments and leaves others comparatively bare. But every so often, the scale of that barrenness feels almost unsettling. One of the most haunting examples lies in the direction of the constellation Eridanus, where observers identified an enormous cold region in the cosmic microwave background, the faint afterglow of the early universe. This patch of sky was not simply darker in the ordinary sense. It appeared cooler than surrounding regions, as though something immense and poorly understood had interrupted the expected pattern. One explanation pointed toward a supervoid, a colossal stretch of space with fewer galaxies than it should contain, large enough to affect the ancient light passing through it. Yet even that answer never felt entirely settled. The difficulty was not just the size, but the implication. The universe, when viewed on its largest scales, is supposed to average out into a kind of statistical calm. Local chaos, yes. Regional variety, certainly. But on the grandest canvas, a rough symmetry. A void too deep or too influential begins to trouble that assumption. It suggests either that our cosmic map is still incomplete or that the rules governing large-scale structure may hold subtleties we have not yet learned to read. There is something profoundly human about our discomfort with absence. We fear silence in a house once full of voices. We feel the weight of an empty chair more than the shape of the room around it. In the same way, cosmic emptiness unsettles us because it refuses to remain neutral. It asks to be interpreted. Was this void simply an extreme but natural feature of an evolving universe? Or was it a reminder that even nothingness can become a kind of evidence? The longer we look outward, the more we discover that emptiness is never truly empty. It shapes motion, bends light, frames matter, and directs attention. Perhaps that is why these vast hollows stay with us. They challenge the old instinct to equate reality only with what is visible, measurable, and full. Sometimes the missing pieces are not gaps in the story. Sometimes they are the story, waiting for us to understand why absence can feel so immense. What if the universe's strangest secret was not something we found, but something we kept failing to see? In the early 20th century, astronomers began measuring the motion of galaxies with increasing precision. They expected the outer edges of these vast star systems to move more slowly than the inner regions, just as planets farther from the Sun travel with a different rhythm than those close in. Gravity, after all, was thought to be an honest accountant. It should reveal how much matter is present by the way objects move around it. But the numbers refused to settle into that familiar logic. Galaxies were spinning too fast. Their outer stars, instead of drifting more slowly, moved as though gripped by far more mass than telescopes could detect. The visible matter, stars, gas, dust, all the shining substance of the known cosmos, simply was not enough to hold them together. By every conventional expectation, these galaxies should have loosened and flown apart, yet they remained intact, turning in silence, faithful to a gravity that seemed to come from nowhere. This was not a small error at the edges of a calculation. It appeared again and again, in system after system, across the sky. Clusters of galaxies showed the same discrepancy. Light bent around invisible mass through gravitational lensing, tracing shapes that could not be explained by luminous matter alone. The evidence accumulated with the quiet force of repetition. Something unseen was there, not as a metaphor, but as a measurable influence, acting across the universe. Scientists named it dark matter, which is both useful and revealing. The phrase sounds definitive, but in truth, it describes a problem more than a solution. It tells us that something does not emit light, does not interact in ordinary ways, and yet exerts gravity on a cosmic scale. It is a label for presence without image, for weight without form. We can map its effects, estimate its abundance, and build models around it. But we still do not know what it is. There is a humbling intimacy in that uncertainty. Much of human life depends on things we cannot see directly: memory, trust, grief, time. We recognize them through consequence. Dark matter belongs to that same strange category, though on a scale almost beyond comprehension. It reminds us that visibility is not the same as reality, and that some of the strongest forces in existence announce themselves only through what they move, hold, and refuse to let go. So the universe turns, and within its turning is a lesson we are still learning. Not every truth arrives in light. Some remain hidden, shaping everything around them, asking whether our deepest misunderstanding has always been the belief that what matters most must first be visible. What if the greater mystery was not the hidden mass that holds the universe together, but the unseen force pulling it apart? For much of the 20th century, the story of the cosmos seemed to follow an intuitive arc. The universe had begun in unimaginable heat and density, then expanded outward in all directions. The real question, scientists thought, was how that expansion would end. Would gravity slowly overcome the outward rush and bring everything back together? Would the cosmos thin out and cool forever? Even uncertainty felt contained within a familiar framework. Expansion was expected. Deceleration was assumed. Then came a result so strange, it first sounded like a mistake. By studying distant supernovae, astronomers found a way to measure not only how far away certain galaxies were, but how the expansion of the universe had changed over time. These exploding stars served as cosmic mileposts, brief and brilliant signals sent across billions of years. When researchers compared their brightness and redshift, the pattern pointed towards something astonishing. The universe was not slowing down. It was accelerating. It is difficult to overstate how unsettling that realization was. Gravity, the great organizer of matter, should have been applying the brakes. Every galaxy should have felt the combined pull of every other. And yet the larger the universe became, the faster space itself seemed to stretch. It was as if the fabric of reality carried within it a quiet pressure, one that only revealed itself when the cosmos grew large enough for its influence to dominate. Scientists gave this mystery a name: dark energy. As with dark matter, the term is less an answer than a placeholder around an absence in understanding. It describes the observed acceleration, the behavior of the universe on its grandest scales, but not the underlying essence of what drives it. Is it a property of empty space? A cosmological constant Einstein once introduced and later regretted? A sign that our understanding of gravity is incomplete? Each possibility opens a door and leaves another unopened. There is something almost philosophical in this discovery. Human beings spend so much of life imagining stability, foundations, things that hold. Yet here is a universe whose largest motion may be governed by something expansive, diffuse, diffuse, and nearly impossible to grasp. Not a center, not a wall, not a visible engine, but a deep tendency towards separation. And still, the galaxies continue their slow retreat, carrying light away from light. In that vast outward drift lies a difficult kind of beauty. The universe is not only stranger than we expected, it may be stranger in the direction of openness itself, forever widening the distance between what we know and what remains just beyond the reach of thought. What if the universe did not simply hide things from us, but occasionally built objects that seemed to violate the rules we thought were settled? Deep in space, astronomers have found worlds that circle dead stars, planets that should not have survived the violence that came before them. A star exhausts its fuel, swells into a red giant, and engulfs the inner reaches of its system. Later, what remains may collapse into a white dwarf, a dense stellar ember no larger than a planet, or into something even harsher. By all ordinary expectation, that should be the end of any nearby delicate order. Whatever once orbited close should be burned, broken, or thrown into darkness. And yet the evidence keeps suggesting otherwise. There are planets that seem to have endured impossible transitions, and others that may have formed again from the wreckage, as if creation can follow devastation without asking permission from our neat timelines. Some orbit pulsars, the rapidly spinning remnants of exploded stars, places bathed in radiation so extreme they once sounded like the least likely homes for planets in the universe. The first confirmed exoplanets ever discovered were found in exactly such a place. It was a revelation that arrived almost as a contradiction, not around a warm, ordinary sun, but around a stellar corpse. The shock was not only scientific, it was imaginative, and we had assumed that planets belonged to stability, to long seasons of gradual formation around living stars. Instead, the cosmos offered a harsher lesson. Worlds can emerge in aftermath. Structure can return where catastrophe has already passed. The universe may be far less sentimental about beginnings than we are. Of course, researchers are careful in how they interpret these systems. Each observation carries uncertainty. Some planets may be survivors, others latecomers assembled from debris disks left behind after stellar death. The details matter, and science advances by resisting the urge to turn anomaly into myth. But even the cautious version of the story is extraordinary. It tells us that our models of planetary history must make room for resilience, repetition, and second acts written under conditions once dismissed as absurd. Perhaps that is why these worlds linger in the mind. They do not merely expand a catalogue, they disturb a deeper instinct. The belief that destruction is always final, that some thresholds cannot be crossed and returned from. Yet across the galaxy, there are signs of orbit after ruin, motion after fire, new geometry after collapse. And maybe that is part of the universe's quiet wisdom. It does not promise safety. It does not preserve what was. But again and again, it shows that endings and origins are sometimes separated by less than we think. A dead star still casts influence. Broken matter still gathers. And in the cold distances beyond our habits of reason, worlds continue to circle what should have left nothing behind. What if some of the universe's most unsettling objects are not the ones that destroy matter, but the ones that seem to erase meaning itself? A black hole is easy to describe in outline and almost impossible to hold in the mind. It begins with mass, collapse, and gravity taken to an extreme from which even light cannot escape. That much has entered public imagination. But beyond the familiar image of a dark sphere floating in space lies something far more disorienting. A place where our best theories stop agreeing with one another. General relativity describes the black hole as a deformation of space-time, a region where gravity curves reality so severely that all paths lead inward. Quantum theory, on the other hand, governs the smaller scales with astonishing accuracy. Each framework has transformed modern science. Each has survived test after test. Yet at the heart of a black hole, where immense gravity meets the smallest dimensions, these two great triumphs begin to speak incompatible languages. Then came an even more troubling question. If something falls into a black hole, what happens to the information that defined it? In quantum mechanics, information is not supposed to vanish. The deep structure of reality, as far as the theory suggests, preserves it. But black holes appear to challenge that promise. When Stephen Hawking showed that black holes may slowly radiate energy and eventually evaporate, the paradox sharpened. If the black hole disappears, does the information disappear with it? Or is it somehow encoded, transformed, hidden at the edge of the event horizon in ways we do not yet understand? This is not abstract confusion for its own sake. It touches one of the oldest human desires, the belief that what has been cannot simply become nothing. We feel this in memory, in history, in the fragile insistence that lives leave traces. The black hole information paradox echoes that longing in mathematical form. It asks whether the universe ultimately keeps account of all that enters it, or whether there are places where reality itself forgets. Physicists have proposed bold answers: holographic principles, quantum entanglement woven into space-time, firewalls, soft hair, hidden encodings. Each idea reveals brilliance. None has closed the matter in a way that satisfies everyone. And so the black hole remains not just an object in space, but a mirror held up to science itself, reflecting both its power and its incompleteness. Perhaps that is why black holes continue to haunt the imagination. They are not merely cosmic traps. They are boundaries around thought, reminders that even our most successful descriptions of the universe may still be fragments of a larger language. And somewhere beyond that dark horizon waits a question more intimate than physics alone. When something disappears from sight, has it ceased to exist, or only moved beyond the limits of how we know how to remember? What if the universe is filled with events so violent that, for a brief instant, they outshine almost everything else, and yet still leave us unsure about what we have truly witnessed? Gamma-ray bursts arrive like messages written in lightning. They are the brightest explosions known in the cosmos, flashes of energy so intense that for a few seconds they can release more power than the sun will emit across its entire lifetime. Yet they do not begin with spectacle in the human sense. They begin as numbers on a detector, as a sudden spike in a satellite's instruments, as a burst of high-energy photons crossing unimaginable distances to reach a machine orbiting our small planet. When they were first detected, they seemed almost impossible to to place. The signals appeared without warning and vanished before anyone could easily trace their source. For years, astronomers did not know whether these eruptions came from nearby within our own galaxy or from the deep universe far beyond it. The uncertainty itself became part of the mystery. A phenomenon this powerful should have been easier to explain. Instead, it arrived as a riddle, brief, random, and overwhelming. Over time, patterns emerged. Some bursts were long, lasting more than a couple of seconds, and seemed connected to the collapse of massive stars, dying in catastrophic explosions that give birth to black holes. Others were short, sharp, and increasingly linked to collisions between neutron stars, the dense remnants of stellar death spiraling together until impact. These interpretations were supported by afterglows, host galaxies, and in some cases, even gravitational waves. The mystery narrowed but never fully disappeared, because even when we understand the mechanism, the experience of the fact remains astonishing. Somewhere, long before human civilization existed, two dead stars may have circled each other in silence, closing the last distance in a final embrace of gravity. Somewhere else, a giant star may have spent millions of years building toward collapse, only to end in a burst so bright that its signal would travel across billions of years to touch our instruments for a moment and be gone. We witness not the event itself, but its late arrival, the delayed echo of forces that have already spent themselves. There is something deeply moving in that delay. We live by old light. We learn from aftermath. The universe reveals itself not in real time, but through messages that have crossed distances too large for intuition. And perhaps that is why gamma-ray bursts feel like more than data. They remind us that reality is constantly unfolding beyond our immediate senses, and that our knowledge often comes as an interruption, a sudden brightness inside a much longer darkness. So we keep watching the sky, attentive to these brief eruptions that vanish almost as soon as they appear. They tell us that destruction can be visible across the breadth of the cosmos, that endings can announce themselves with extraordinary clarity, and that even the shortest event can carry a story older than our species. The question is never only what exploded. It is also what kind of universe makes such violence possible, and what it means that we can understand part of it, yet still feel awe before the rest. What if the strangest thing in the universe is not what burns, collapses, or explodes, but what we can hear only when space-time itself begins to tremble? For most of human history, the cosmos reached us through light. We studied stars by what they emitted, galaxies by what they reflected, nebulae by the colors spread through telescopes and glass. Even our most advanced instruments were, in essence, refinements of sight. Then, in the early 21st century, something remarkable happened. We learned to listen to the universe in an entirely different way. Gravitational waves had been predicted long before they were observed. Ripples in space-time produced by massive objects accelerating through the cosmos. Einstein's equations allowed them, but for decades, they remained almost impossibly faint, more mathematical consequence than measurable fact. To detect one required instruments of extraordinary delicacy, capable of sensing distortions smaller than the width of a proton across kilometers of space. It sounded like a dream, balanced on the edge of absurdity, and yet the signal came. In 2015, two black holes collided more than 1 billion light-years away, releasing energy in a final merger so immense that it briefly radiated through space-time itself. By the time that disturbance reached Earth, it was unimaginably subtle, a passing shiver through reality. Still, detectors caught it. What they recorded was later translated into sound, a short, rising chirp, almost modest in its human scale. But contained within that tiny note was the violence of warped space-time, the signature of an event no eye could have seen directly. The discovery changed more than a field of physics. It changed the mood of inquiry. Suddenly, the universe was not only visible, but audible in a profound sense. Collisions between black holes, mergers of neutron stars, catastrophic events hidden from ordinary telescopes could now be traced by the waves they sent through the fabric of existence. We had not merely sharpened an old tool, we had opened a new sense. There is something deeply moving in that transition. It suggests that reality has always been richer than the channels through which we first encountered it. How many truths have passed around us unheard simply because we lacked the means to receive them? Human understanding often advances this way, not by replacing one vision with another, but by discovering that the world has been speaking in more languages than we knew. So the cosmos hums and shivers, and now, at last, we are beginning to notice. In those faint, gravitational echoes lies more than scientific achievement. There is a quieter lesson as well, that the universe is not obliged to reveal itself in forms familiar to us. Sometimes it waits until we build the patience, humility, and imagination required to hear what was always there, moving silently through the dark. What if the oldest light in the universe is not merely a relic of the past, but a surface on which time itself has left small, troubling fingerprints? Long before stars formed, before galaxies arranged themselves into filaments and clusters, the universe was a hot, dense ocean of particles and radiation. Nothing could travel freely. Light scattered constantly, trapped in a young cosmos too crowded to become transparent. Then, as space expanded and temperatures fell, a threshold was crossed. Atoms formed. Radiation broke free. That ancient glow still surrounds us today as the cosmic microwave background, a faint whisper from a time when the universe was less than 500,000 years old. At first glance, it seems almost uniform, remarkably smooth across the sky. But the more carefully scientists measured it, the more subtle irregularities emerged. Tiny fluctuations in temperature, minute differences in density, the earliest seeds from which later structure would grow. These variations are not flaws in the data. They are the first rough notes of the cosmic composition, the beginning of all later complexity. Without them, there would be no galaxies, no stars, no planets, no us. And yet within that precious map of the early universe, certain anomalies continue to stir debate. There are patterns that seem slightly misaligned with statistical expectation. Hemispheric asymmetries, unusual alignments in large-scale fluctuations. The cold spot, a region of sky that appears difficult to fold neatly into the simplest models. None of these features, on their own, overturn the foundations of cosmology. Scientists are careful, as they should be. Randomness can produce surprising arrangements. Data analysis is vulnerable to overinterpretation. The line between meaningful anomaly and human pattern-seeking is thin, especially when the sample is the universe itself. Still, the unease remains valuable, because these faint irregularities remind us that even our clearest window into cosmic origins is not a finished portrait. It is a record filtered through instruments, models, assumptions, and the stubborn fact that we observe from within the system we are trying to understand. We do not stand outside the universe looking in. We read its earliest light from deep inside its later consequences. There is something humbling in that position. We are creatures of the afterglow, trying to reconstruct beginnings from faint temperature differences scattered across the sky. The oldest light does not speak plainly. It offers hints, textures, probabilities. It tells us that order emerged from slight imbalance, that everything enduring may have started with almost nothing at all. But it also leaves room for hesitation, for the possibility that the universe's first visible face still contains expressions we have not yet learned to read. So we study the afterglow with increasing precision, knowing that each refinement brings both clarity and new uncertainty. And perhaps that is fitting. Origins, whether cosmic or human, are rarely simple once examined closely. The deeper we look into the first light, the more we discover that even the beginning was not pure simplicity, but a field of delicate imperfections from which all wonder would eventually arise. What if the most unsettling possibility is not that the universe hides monsters in the dark, but that reality itself may be more provisional than it appears? Modern physics has revealed a world far less solid than human intuition once imagined. At the smallest scales, particles behave like probabilities until measured. Empty space seethes with temporary fluctuations. Fields, not objects, may be the deeper furniture of existence. Even the vacuum, that word we casually associate with nothingness, is no simple void. It is structured, active, and perhaps less permanent than it seems. This idea becomes especially haunting in theories about vacuum decay. According to some interpretations of particle physics, the state of the universe we inhabit may not be the absolute lowest energy state possible. It may be stable only in a local sense, like a ball resting in a shallow valley, while a deeper one lies elsewhere beyond a hidden ridge. If that were true, then reality as we know it could, in principle, transition to a more stable configuration. Not gradually, not with warning, but through a bubble of altered physics expanding at nearly the speed of light. The concept sounds like science fiction because it touches a fear older than language, that the ground beneath ordinary life is not guaranteed. Yet what makes the idea powerful is not sensationalism, but restraint. Physicists do not speak of it as prophecy. It is a theoretical possibility arising from the mathematics of fields, symmetry, and stability. The universe has persisted for billions of years, which itself suggests either that such a transition is extraordinarily unlikely or that our current vacuum is far more secure than some equations allow. Still, the fact that the question can be asked at all changes something in the imagination. Because beneath the technical details lies a philosophical tremor. We build our lives on continuity. We assume the constants will remain constant, that matter will keep its shape, that tomorrow will honor the same physical grammar as today. Vacuum decay challenges that instinct at the deepest level. It imagines a cosmos in which the laws we treat as eternal may themselves be contingent, temporary expressions of a larger and less settled order. And perhaps that is why the idea lingers, even for those who never study the equations. It reminds us that stability is often a lived experience, not an absolute guarantee. Human history, memory, institutions, even identities carry the same paradox. They feel durable from within, yet they rest on conditions that can change. So the universe continues around us in dependable silence, atoms holding, stars burning, light traveling according to familiar rules. And maybe that is enough. Maybe the deeper lesson is not to fear hidden collapse, but to recognize how extraordinary it is that reality has held together long enough for beings like us to notice it at all. In that awareness, there is both humility and wonder, the realization that existence may be more fragile than it appears, and more miraculous for exactly that reason. What if the universe does not simply contain strange objects, but imposes limits so absolute that they begin to feel like the edges of thought itself? Every age has imagined that one more instrument, one more voyage, one more refined theory might finally bring the whole of reality into view. And in some ways, that faith has carried us far. We have measured the age of the cosmos, traced the lives of stars, detected planets around distant suns, and listened to the faint trembling of space-time. Yet the farther knowledge reaches, the more clearly another truth comes into focus. The universe is not only vast, it is bounded by horizons. Some of those boundaries are practical. Light travels at a finite speed, and the cosmos has existed for a finite time. That means there are regions so distant their signals have not had time to reach us. Beyond the observable universe lies not necessarily emptiness, but simply what we cannot yet see. Other limits are more intimate. The Planck scale marks a realm where our current theories lose their confidence. The interiors of black holes remain hidden behind horizons we can describe mathematically but not penetrate. Even the earliest moment of cosmic origin still resists any complete account. These are not failures of curiosity. They are structural features of the reality we inhabit. There may be truths forever outside our observational reach, not because we are lazy or unworthy, but because the rules of the universe do not permit total access. That idea can feel unsettling in a culture shaped by progress, where every mystery is expected to become a problem solved by better tools. But perhaps wisdom begins where mastery ends. There is a quiet dignity in recognizing a horizon. Sailors once understood that the line where sea met sky was not an insult, but an invitation to continue with care. Human life is full of similar boundaries. We cannot fully know another mind. We cannot recover every lost moment. We cannot stand outside our own mortality and inspect it from safety. Yet these limits do not empty life of meaning. Often, they deepen it. So too with the cosmos. The existence of unreachable regions, hidden interiors, and ultimate scales does not diminish the beauty of science. It clarifies its role. Knowledge is not possession. It is relationship. We do not conquer the universe by understanding part of it. We enter into dialogue with it, question by question, measurement by measurement, aware that some answers may remain beyond the horizon. And maybe that is the final shape of maturity, in science as in life. Not the fantasy of knowing everything, but the ability to keep looking with honesty, even when the edge of visibility stays where it is. The universe gives us light, patterns, and clues. It also gives us distance. Between those two gifts, wonder survives. What if the deepest lesson of all these mysteries is not about the universe alone, but about the kind of beings we become when we try to understand it? Across observatories, laboratories, deserts, mountaintops, and orbiting instruments, the work of discovery is carried forward by ordinary human persistence. Not by certainty, and rarely by sudden revelation, but by people adjusting mirrors in the cold, calibrating detectors after midnight, arguing over anomalies, checking equations again, and learning how to doubt their own excitement without surrendering it. Behind every cosmic mystery is a profoundly human scene, someone noticing that a number does not fit, that a signal arrived too early, that a pattern bends away from expectation. This is easy to forget when we speak of black holes, dark matter, gravitational waves, or the first light of the universe. The language can sound vast and impersonal. But science is never only about objects. It is also about attention, patience, and the moral discipline of not claiming more than the evidence can bear. In that sense, the search for truth in the cosmos is inseparable from character. It asks us to remain imaginative without becoming reckless, skeptical without becoming cynical, humble without becoming passive. There is beauty in that balance, especially now, in an age flooded with noise, speed, and declarations. The scientific encounter with mystery offers another model of intelligence. It shows that not knowing is not a weakness to be hidden. It can be a form of honesty. A star dims in an impossible way. A galaxy spins too fast, and a patch of ancient sky looks colder than it should. The mature response is not immediate myth nor empty dismissal, but a longer kind of listening. Perhaps this is why cosmic mysteries feel so personal. Even when they unfold at unimaginable distances, they mirror our own unfinishedness. Human beings also live among partial explanations. We inherit stories, test beliefs, revise memories, and move through lives where some truths arrive late and others never fully resolve. We, too, are creatures of fragments, trying to assemble coherence from scattered signals. And still, we continue. We build telescopes. We refine theories. We send instruments beyond Earth and train them back toward the dark. Not because we expect the universe to become simple, but because the act of seeking changes us. It widens the self. It teaches proportion. It reminds us that confusion is not the opposite of wonder, but often its doorway. So, before this journey closes, one truth stands quietly above the rest. The cosmos is not only a field of mysteries, it is a school for attention. And in learning to face what we cannot fully explain, we may be learning something just as important about ourselves: how to live with awe, how to remain honest before the unknown, and how to keep searching without demanding that the universe shrink to the size of our certainty. So where does all of this leave us? After the dimming stars, the invisible mass, the accelerating void, the trembling fabric of space-time, the relic light, and the horizons we cannot cross, it leaves us, perhaps, where every serious encounter with the universe finally arrives, not at certainty, but at perspective. The cosmos is not a machine that has failed because we do not yet understand every part of it, nor is it a theater built to frighten us with its scale. It is something more difficult and more generous than either of those ideas. It is a reality vast enough to exceed our categories, patient enough to reveal itself in fragments, and subtle enough to reward the long discipline of attention. The most haunting things we have explored were never simply space horrors, though they may have stirred that old emotional register in us, the shiver that comes when familiar order begins to loosen. In a deeper sense, each mystery has been a lesson in proportion. Dark matter reminds us that the visible is not the whole. Dark energy suggests that the largest movements in existence may be driven by causes we barely know how to name. Black holes confront us with the limits of theory. Ancient anomalies in the afterglow of creation tell us that even origins may resist complete clarity, and every horizon, whether physical or conceptual, teaches the same quiet truth. Knowledge is powerful, but it is not possession. Yet none of this should push us toward despair. Quite the opposite. There is something profoundly human in continuing to ask, even when the answers remain partial. We are a species that rose on one small world and learned to read signatures in starlight, to hear collisions in space-time, to infer invisible structures from the motions of galaxies. That is not failure. That is extraordinary. Maybe the final insight is this: Mystery is not a flaw in our story of the universe. It is part of the story's meaning. It keeps arrogance from hardening into dogma. It keeps curiosity alive. It reminds us that reality is not exhausted by our current language, and that truth often arrives not as conquest, but as relationship, built slowly between the unknown and the patient mind. And so we end where we began, under the same sky that first invited questions from our ancestors. The stars remain. The darkness remains. Our instruments grow finer, our models more elegant, our maps more detailed. But beyond every new answer waits another edge, another silence, another possibility. Perhaps that is the gift. Not that the universe yields completely, but that it continues to call us forward, asking what kind of wisdom we might build from wonder, and what kind of future becomes possible when we learn to face the unknown without turning away.